We'll now talk about section 6.3, which is binomial and geometric random variables. And a binomial situation is when you've got, in essence, a proportion. All right, you've got, in essence, a probability. And so let's say you've got like a scenario where, let's say, 40% of people in a town own a house. And then it'll say if you take a sample of 5 of the people, what is the probability that you will have, let's say 3 of them out of the 5 own a house. And so you're going to have this scenario where you have a probability and then a number of trials. And so when you've got that, you've got the potential to have a binomial situation, and it's going to ask about the certain probability of a number of successes. So, this could be, for instance, you've got, let's say, a truckload of potatoes, and, and 40% of them are, let's say, rotten. And you take a sample of 5 of the potatoes. What's the probability that exactly 3 of them will be rotten? Or if 40% of people in a town are against some amendment that they're voting on, you randomly select 5 people. What's the probability that 3 of them are going to be against the amendment? That sort of thing. So it's this sort of scenario. You're always looking for your P and your N and your X, and the P has to stay the same the whole time. But so hopefully we can do some examples here, and it'll be clear what's going on. But the first thing is properly identifying a binomial setting. And to do that, there's really 4 conditions. And your book uses the acronym BINS. And so we'll use that. And the B is binary. In other words, it has to be a success-failure situation. It has to be just 2 options. It has to be, like either they own a house or they don't own a house, or someone is a Republican or they're not a Republican. It can't be a thing where there's 3 options. Someone's a Republican, Democrat, or other. If that's the case, it's not binomial. So it has to be just a success-failure situation. Then we have independence. That's going to be an important issue for us the rest of the year. In essence, knowing one outcome tells you nothing about the probability of the next outcome. In essence, most of the time, it's pretty much that your probability stays the same. Like in the examples we were talking about, it stays in essence at 40%. N is for number of trials. Number of trials is that you have a fixed number of trials you're looking at. Like in this one, we had a fixed number 5 that we're looking at. And so it'll say in these problems, it'll say, there's a certain proportion in a population. Then it'll say, we look at 5 of the people or things. And so that is a fixed number of trials that we're looking for. And then the S is, in essence, the same proportion every time. The same proportion every time. And that is sort of very similar to this independence. In essence, like in this situation, with each trial, it has to stay at 40%. And so that's what we're looking for a binomial situation. You look for the proportion, a success-failure situation, a fixed number of trials. The proportion doesn't change, and that the trials are independent. The outcome of one is in no way associated with the change in the probability of the other one. Now, and we've got 3 formulas that look kind of complicated that are on our formula sheet, but they're not that hard to use. And so this, in understanding these things, is really, going through examples, I think will hopefully, clarify this. This is how you make a calculation of a binomial probability. So for instance, in this particular one, so the probability that X is equal to K. And X is, in essence, always going to be your number of successes. So in this situation where your N is 5, your probability of success is 0.4, and your N is 5, you could have conceivably 0 successes, 1, 2, 3, 4, or 5 successes. But we're looking for the probability of that X is 3 successes. And so what that is going to be, this notation, and you may have had this notation in another math class, is what we're going to call 5 choose 3. It's the number of ways you can, in essence, select 3 objects from a group of 5. Right? And so then we'll multiply this, and it says the probability of success is 0.4 to the power of 3, and then times 1 minus that, which would be 0.6, and then 5 minus 3, or 2. So what this formula is saying here all right, what's the probability we're going to have 3 successes? Well, the probability of success is 0.4. So the probability of that happening 3 times is 0.4 to the third power. And, the probability of failure is 0.6. Well, we're saying that failure is going to happen twice. And this is the number of ways that, in essence, can sort of be rearranged. Because it could be that your successes are on the first, second, and third person, and then you fail on the fourth and fifth, or it could be the first, second, and fourth, or the first, second, and fifth. This is the number of ways we can rearrange it. Now, this notation, what this is right here, is this 5 choose 3. Sometimes you'll see it written like this, 5 choose 3. And what it's equal to is 5 factorial over the difference factorial, and then 3 factorial. Okay, so it's just 5 factorial over that factorial and the difference factorial. And so that is in essence 5 times 4 times 3 times 2 times 1. And so if we were to, in essence, do this by hand, so that's going to be 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1, and then 3 factorial is 3 times 2 times 1. Well, we can cancel things out. 3 times 2 times 1, 3 times 2 times 1. And then 5 times 4 is 20, and then 20 divided by 2 is 10. So that's 10, and then the rest of this be 0.4 to the third power times 0.6 to the second power. And so let's find what this particular thing is. And so I will just say 0.4 to the third power. So I'll go 0.4, and then that is your exponent button, that up arrow. So we hit up arrow to the third power, and then right arrow over, and then times, and then it's 0.6 squared. So it'd be 0.6, and just hit the squared button like that, is equal to, and then just multiply it by 10. So times 10, and so that is 0.2304. So that is 0.2304. So there's about a 23% chance that, and whatever the context is here, that if, like, let's say 40% of people in a city own a house, if you randomly select 5 of them, what's the probability that exactly 3 of the 5 own a house? So that's the question that is answering. And then we've also got a shortcut with your calculator in that regard, but that's how you do a binomial calculation by hand using that formula. And that's on your formula sheet. And so here's how you calculate a mean. It's just going to be n times p. And I think that one's going to be pretty intuitive there. So you can see it there, n times p. And then the binomial standard deviation is that. So we'll plug that in to find the standard deviation. Both those are on your formula sheet. And then before we look at some examples, another important issue is the fact, in general, our population size has to be at least 10 times our sample size. Because the thing about it is we rarely use replacement when we're doing sampling. So that could conceivably change our proportion. So for instance, like let's say if there's 100 people in our sample, 100 people in our population, and 40% of them own a house. So the probability that the first person is going to own a house is 40 out of 100. Well, given the first one owns a house, the probability the next one's going to own a house is 39 out of 99, and so forth. And so given that the first 2 own a house, the probability the next one's going to own a house is going to be 38 out of 98. Well, if your population is big enough, all right, it's not going to change significantly by not using replacement. So, but if it's too small, then your proportion is going to change and will violate that condition of the proportion remaining roughly the same. So this is what in essence needs to be true. When taking a simple random sample of size n from a population of size big N, we can use a binomial distribution to model the count of successes in a sample as long as our sample size is less than or equal to 1/10 of our population size. In other words, the population size has to be at least 10 times the sample size. That ensures us that even if we don't use replacement, our proportion will stay the same. Okay, so anyway, let's go ahead and look at a context. I think the best way to understand this stuff is by looking at some examples. And so in context 1, Fritz plays basketball. Each time he takes a free throw, there's a 60% chance he'll make the free throw. He takes 4 free throws. So all these problems are the same in essence. You're going to have a given proportion which is 0.6, so I'll go ahead and write that. And then we have a given number of trials. In this case, n is equal to 4. Is this a binomial setting? And we have our 4 things. First of all, it is a success-failure situation. Either he makes the free throw or not, so it is binary. So that is met. Independence. Now, it clearly says that every time he takes a shot, there's a 60% chance he makes it. It's not like that he makes a couple in a row and he starts feeling more confident and the proportion goes up, or he misses a couple in a row and his confidence goes down and he becomes more likely to miss it. No, there is a 60% chance. So we every single time. So the trials seem to be operating independently. So therefore that is met. And so fixed number of trials. So we have a fixed n is equal to 4. He's taking 4 free throws. And then lastly, the proportion never changes. P is equal to 0.6. And like I said, that's really similar to this thing, and I'm not going to get into big time, when those are in essence different. But the main deal is the proportion never changes. You get a fixed number of trial, and you get a set proportion there. So therefore, yes, it is. All right. So what is the probability he'll make exactly 3 of 4? So the situation we have here is we've got, once again, our P is equal to 0.6, our N is equal to 4, and he will make exactly 3 of 4. So therefore, our X is 3. So we will plug it in to this formula here. And so that will be, in essence, 4 choose 3. All right, times, and then 0.6 to the third power. We have 3 successes, and the probability of success is 0.6. So our probability of failure is 0.4, and we have 1 failure. So this is 3 successes, 1 failure, and this is the number of different ways they can happen. In essence, that's going to be 4, because you could have 3 successes and a failure, or you could have 2 successes and a failure, and then a success. In other words, your failure could be your first, second, third, or fourth one. So, by the way, let me show you, first of all, the shortcut to finding 4 choose 3. 4 choose 3 on your calculator is on the math menu. If you go to math and you go over to probability, there it is, the third one down. That's what we call the choose function. It's the number of different ways you can choose, in this case, 4. We can choose 3 objects from a group of 4. So you just enter 4 and 3 into there, and sure enough, that's equal to 4. And so I will now say, okay, 4 times 0.6 to the third power, like that, right arrow over, and then times 0.4 to the first power, and so that is equal to 0.3456. So 0.3456, boom. That's how you do it, all right? The other way of doing it is by using your binomial functions on your calculator. In this case, what we're going to call binomial PDF. Stands for binomial probability density function. And it's important if you use this, and I'll show you where it is you label that N, my number of trials is 4, P, my probability of success is 0.6, and X, my number of success is 3. It's important that you label those with N, P, and X. If you don't label these with N, P, and X, you're going to get, at best, partially correct. All right, so let me show you where those are, where this function is. It's in the distribution menu, which is right above the bars button. So if you go second distribution and you scroll all the way down close to the bottom, there it is, binomial PDF. Okay, CDFs is a different thing. We're going to do that in a minute. Binomial PDF, so we hit enter. And you're going to enter it in that order, 4, 0.6, and 3. So my number of trials is 4, my probability of success is 0.6, my number of successes is 3. So there we go. So, and we get obviously the same answer. But showing your work is making sure to write this down like that. And yes, you can use this thing anytime you want, but you have to know how to use the formula. It's a frequent multiple choice question to include the formula, or it could ask you to show the formula. But you can use binomial PDF to find the values, but make sure and show those things. So this is, in essence, the probability of getting 3 successes out of 4 trials if your probability of success is 0.6. And like I said, all these problems, there's a number of different contexts that could be in, but they're all the same. You're always given a P, some sort of P, some sort of N, and some sort of X. Then it says this, show the distribution of X. So X is always your number of successes. So the distribution of it is that you would list every possible value of it. So X could be, if you shoot 4 free throws, or if Fritz does, there's the possibilities you could have 0, you could make 1, 2, 3, or 4. The distribution of X is just your number of possible successes. So it's always going to be 0 to your total number of n. And so we're going to list every possibility. Now, we already know that the probability of 3 successes is going to be 0.3456. So back in the day when we would just do this by hand, we would just have to do this 4 more times to, in essence, find these 3 numbers. And you can still do that, and you need to know how to do that. But I'm going to show you the shortcut of how to do this whole thing with your calculator. What I'm going to do is I'm going to use this binomial PDF function, but I'm going to do it in a list. And in list 1, I'm going to put the x values here. And then where you're supposed to put the x value here, I'm going to just put list 1 in it. So I'm going to put 0, 1, 2, 3, and 4. So I'm going to go to my list. I'm going to go Stat and Edit. Let me clear all this stuff out by hitting clear and down arrow on the top of the list, like that. And so I'm going to put all my possible x values in list 1, 0, 1, 2, 3, and 4. All right, and then I'm going to highlight the top of list 2, and I'm going to put the binomial probabilities in list 2. So I highlight the top of list 2. Now I'm going to go to binomial PDF. So I go second distribution. I scroll all the way down to binomial PDF. I actually scrolled up and it took me to the bottom of the list. So binomial PDF, I hit enter. And so the number of trials we have is 4. Our probability of success is 0.6. The x value, I just put all the x values in list 1. So I do second list 1 and hit enter. And there it is in the command line right there. And I hit enter and it lists all of the binomial probabilities for me. That is so much easier than just using the formula by hand. And so the probability of 0 successes is 0.0256. So I'll write these down. So 0.0256, and this would be 0.1536. The probability of him making 2 free throws is 0.3456, which is coincidentally the same as him making 3. And the probability that he's going to make all 4 free throws is that. About 13%. So there is the probability distribution. It shows every possible outcome and each probability. And you can make a little histogram out of this. Just put a bar going up for each of these values. And so that's how you do that. Now, find the mean and standard deviation of the number of free throws he's going to make. Because if Fritz were to take 4 free throws many times, it's gonna vary. Sometimes and it's gonna vary like this. I mean, sometimes he's gonna make 2, sometimes he's gonna make 3. Occasionally he'll make 0 out of 4. That's pretty unusual. Occasionally he'll make 4 out of 4. But what is this average? What is the average of this? And it's a simple calculation, and there it is on your formula sheet. The mean of a binomial random variable x is just n times p. And so all you do, you'd say the mean of the x is just going to be n times p. And so that our n is 4 and our p is 0.6. And so thus that is going to be 2.4 right there. And don't round it. Don't round it. Our standard deviation is going to be right there. That is also in your formula sheet. Square root of n times p times 1 minus p. As a matter of fact, let me show you where they are. They're right below what we've just been doing. So this is, of course, chapter 5, those 2 formulas. And here's section 6.1 with the discrete random variable mean, standard deviation. And then it even says it right there. If it has a binomial distributions with the parameters n, number of trials, and p, then there is the binomial formula calculation. There is the mean. There's the standard deviation, and everything below this is in chapter 7. So we certainly aren't worrying about that there. So this is what we're doing right now. And so this would be, this right here would be the square root of n times p times 1 minus p. And so that would be the square root of 4 times 0.6 times 1 minus that, which would be 0.4. And that, in fact, is equal to 0.979796. So there we go. And so that's how you calculate the mean and standard deviation. So the next question is this. So the next question is, what do these values mean? And to be able to interpret them. And that is a dominant theme in the AP exam. It's something we did in Chapter 1, and we did it in Section 6.1 as well, is being able to state what these things mean in context. What they mean in context is this, is if we were to look at a large number of trials. In other words, if we were to have Fritz take 4 free throws again and again and again, we're expecting him to make, on average, 2.4, and don't round the number. Okay? Standard deviation. If we were to have Fritz take 4 free throws many, many times, again and again and again, we would expect the number of free throws he makes to vary from the mean by an average of that. So let me go ahead and write that down, and that is, in essence, the next question we have. And like I said, this is, using these formulas and calculations, it is a part of the AP curriculum, and you have to know how to do it, but being able to interpret things in context is in essence kind of much more important. So interpreting the mean, our mu is equal to 2.4. And so to interpret that in context, if Fritz were to take 4 free throws, many times, we expect him to average 2.4 makes. Boom. That is the meaning of the mean. That is how to interpret the mean in context. The standard deviation in context, in this case, 0.9798, I will round that to, stating what is the meaning of it in context. Well, this is the average amount that our points are varying from the middle. And so, but we have to say that in context. If Fritz were to take 4 free throws, many times, we expect the number of makes to vary from the middle, from the mu is equal to 2.4 by an average of 0.9798. Boom. So that's the mean and the standard deviation in context. So, all right, and so then we've got this. So then we've got a situation where we're going to have to find not the probability of one value, but the probability of a number of values, an interval of values. And we're going to use a function called binomial CDF, which was just below the one that we just used in our calculator. And so if he shoots 8 free throws and the probability of success is still 0.6, and that doesn't change, and so it's definitely a binomial situation, what's the probability he makes at most 6? So make sure you don't get mixed up by understanding at most and at least and that sort of thing. Well, let's think about this. What are the possible values of x? And so x is the number of makes. X in every one of these problems is the number of possible successes that you're going to have. All right, and so he's taken 8 free throws. He could make 0, 1, 2, 3, 4, 5, 6, 7, or 8. So the probability that he would make at most 6 includes 6, but it's everything below 6. Now, back in the old days, we would just have to use the formula 7 different times and add these numbers up. Now, and you could do that thing with a list that I did and add those numbers up, but we're going to do what is known as binomial CDF. So binomial CDF, and the C stands for cumulative. It means cumulative density function. Cumulative in stats means that value and everything before it. Everything smaller. It is sort of the concept of a percentile in essence. And so binomial CDF is going to tell us the probability of a certain value or lower than that, and that's exactly what we need here. So we enter in the parameters we enter in. N is equal to 8, our number of trials. P, our probability of success, is 0.6. And then X, our number of success, is less than or equal to 6. So we'll just enter 6 in. Make sure when you're showing your work, You have to write binomial here like that. You have to write n is equal to, p is equal to, x is equal to or less than or equal to in this case to get credit. And so here's where this is in your calculator. So let me get out of the list. I'll do second quit to get out of the list and just clear this out. Then I'll do second vars, which is distribution, and I scroll all the way down to binomial CDF. Don't get those mixed up, please. So binomial CDF. And so my number of trials is 8. My probability of success is 0.6. And then my X values, and this is, since it's CDF, it's going to go 6 and below. And so I entered in like that. Some calculators will immediately take you to this screen, by the way, and that's how you would enter it in. And then so you hit enter, and so that would be 0.8936, which I believe is correct, according to my records. Yes, it is. And so this would be equal to 0.8936. And so, in other words, probably so. We would expect Fritz, if he takes 8 free throws, almost 90% of the time, he's going to make 6 or less. So 10% of the time, by the way, he's going to make 7 or more, right? Actually, about 10.64% of the time, right? So anyway, which that leads me to the next thing. All right, if Fritz were to take 8 free throws, what's the probability he'll make at least 4? So let's think about what our possible values of x here. It could be 0, 1, 2, 3, 4, 5, 6, 7, or 8. At least 4. That includes 4. Like that. Now, the problem is our binomial CDF function is cumulative. It always tells us the probability of a certain value or below it. But we need the probability of 4 or above. So what we're going to do is we are going to find the probability of 3 or below and then subtract it from 1 because something has to happen. He has to make somewhere between 0 and 8 of these free throws. So when you add up all of the probabilities of each of these numbers, they have to add up to 1, like with that other probability distribution we were looking at. It has to add up to 1. So the way we're going to do it when it has the probability of something or more, like at least, I'm going to do 1 minus the probability that won't happen because binomial CDF can tell us this value. And so therefore, our answer is going to be 1 minus, and I'll do binomial CDF, where my n is equal to 8, my p is equal to 0.6, and my x is less than or equal to 3. And so when you do that, so what the heck, let's do that. So I will do second distribution, and I go down to binomial CDF. And so we are going 8 and 0.6, and my x value is 3, so it's CDF 3 or less. So the probability of 3 or less is 0.1737 approximately. So that's going to be 1 minus 0.1737. And so that, in fact, is going to be equal to 0.8263. So when you're trying to find the probability of a certain value or above it, you find the probability of a certain value below it and you subtract. Okay, that's about everything that can happen to you in regards to binomial situations. The other type that we're not going to spend near as much time on is what is known as a geometric random variable. Geometric also deals with the 4 conditions. You have to have, in essence, a set probability. You have to have a success-failure situation. So it can't be a thing where there's 3 outcomes. It's got to be either, a win or a loss, a made free throw or a missed free throw, or someone, gets the part in the school play or they don't get the part in the school play. That sort of thing. Similarly, we have to have independence. The probability, in essence, has to stay the same. So we have, in essence, the same proportion for every trial. Same proportion for every trial. And then lastly, this is what makes geometric different in essence, sort of from binomial. Well, first of all, we don't have, in essence, a fixed number of trials, but is that the variable of interest is when is your first success. That is what it's going to ask you. So right when you see, when is the first success, you're going to say, aha, this is a geometric situation. So it could be a situation like here where you have to find someone to fill a job. You just need 1 success. I mean, the question isn't, well, if you interview 5 people, what's the probability you're going to have 3 of them that work out? You don't need 3. You just need 1. All right? Or, let's say you're trying to get a seat on a plane and you're on standby. You just need one seat. So your concern is, when is your first success? Or it could be, failures of systems. It could be like, what's the probability a plane part is going to break? Well, it just has to happen one time, and then the plane's going to crash, and it'll all be over. So when it's a situation where, when is your first success? And your book has good examples and problems to look at. And here's the formula. These things actually, believe it or not, are pretty intuitive. So this is the formula we're gonna put it in. What's the probability your first success is on the kth trial? And we'll just plug it into that. It just means you have k minus 1 failures and then a success. This is the probability that it will be on and after a certain number of trials, and there's a little formula. And by the way, these formulas aren't on your formula sheet. So the gurus are, in essence, expecting you to understand what I'm fixing to say intuitively. If they were going to ask you to find the standard deviation of the situation, and I didn't even put the formula here, it's not on your formula sheet, so that would be an unusual problem, but if they did, they would have to give you that formula. The mean is just 1 over p. That's certainly an easy calculation if you know what you're doing. So let's look at this context. So Gustav is looking for someone to fill a job opening in his axe factory. Each time he interviews someone from the field of applicants, there's a probability of 0.1. There's our fixed probability that he will interview an applicant that is qualified for the job. So it says clearly there that it's 0.1 every time, in essence, and that never changes. So that meets our condition. It is a success failure. Either they're qualified for the job or not, so that's good. And we are concerned with, when is the first applicant, and so when is the first qualified applicant occur? So that makes it a geometric setting. What's the probability that the first qualified applicant that Gustav interviews would be the 7th one? What that means is, if the first success is on the 7th one, it means he had to have had 6 failures. He had to have had 6 failures and then 1 success. And then 1 success for the first success to be on the 7th one. Well, what's our probability of failure, in essence, which in this case would be talking to someone who's not qualified for the job? So the probability of failure is 0.9, 1 minus that. So this would be 0.9 to the 6th power. That's the probability of multiple events. You multiply them. So it's 0.9 times 0.9 times 0.9, 6 times. Times the probability of first success. So it'd be times 0.4. So hopefully that's pretty intuitive for you. So, and then you multiply those. And so this is going to be 0.9 to the 6th power. So I will just hit 0.9 and hit the raised to the power of 6, hit enter, and then go times 0.1. And so that gives me 0.053144. And so that is your standard geometric problem, 1441. Boom. There you go. Now, this is not a very common problem, but I debated whether to put an example, but I did. What's the probability that it will take at least 10 interviews? So in other words, 10 interviews or more. 10 interviews or more for Gustav to encounter a qualified applicant for the first time. Because once again, all he cares about is finding 1 applicant. All right, so that makes it geometric. If the first qualified applicant was on the 10th one, well, that would mean he would have, in essence, 9 failures, and then 1 success on the 10th one. And so that is going to be 9 failures would be 0.9 to the 9th, and then times the 0.1. Well, if it was on the 11th one, it could be on the 11th one. And so you would just say, well, that would be 10 failures, and then it would be 0.1 for the 11th one. And you could keep going on. But the thing about it is, when your first success is on the 10th one or after, what we definitely know is that we've had 9 failures. We don't know when the success is. And that is what this little formula is saying. The probability that y is greater than or equal to k, it just means you've had failures 1 less time than that. So if your first success is on the 10th time or after, it just means you've had 9 failures. We don't know when the first success is. And so it's just 0.9 to the 9th. So it's 0.9 to the power of 9. And that, in fact, is equal to 0.3874. So it's approximately equal to 0.3874. Lastly, what is the mean of this distribution? So the mean of a geometric distribution. It's a distribution because there's a number of values. The distribution would be, by the way, if you found the probability of that your first success would be on the first one, or on the second one, or on the third one, or on the fourth one, and you find all those different numbers. So the mean is if we were to do this a large number of times. In other words, if Gustav were to if he were to interview people until he find a qualified applicant, maybe the first time he did it was on the 9th one. The second time he did it was on the 3rd one. The third time he did it was on the 15th one. And he were to do the same procedure many, many times, what would it average? And it's 1 over p. So that would be 1 over 0.1, and so that is 10. So which is an integer, but you would not round these things when you reported them. So in essence, in the long run, we're expecting it to average. And hopefully that makes some intuitive sense, because if there's a 1/10 chance of success, you're expecting on average to get your first success on the 10th trial. So anyway, that's it. That's binomial and geometric. These problems can be a bit challenging, but I hope you enjoyed. I think there's some interesting problems. I encourage you to read your book. Thanks for watching. I wish you much success in binomial and geometric distributions and in everything else.